the wing of a plane. As the plane is traveling forwards, right, you end up with the air traveling over the surfaces here, and the wing is shaped in such a fashion that the air, the streams of the air, right, the lines of airflow, if you will, are concentrated on top compared to below. So notice that there's more spacing here than here, which means the air here is traveling slower than the air above the wing. Since the air above the wing is traveling faster, there's a pressure difference. Above the wing, the airplane's wing, the air is traveling faster. Since it's traveling faster, it's a lower pressure here compared to the higher pressure down here, and that lifts the wing. And so if you're chewing gum and baling wire and all these things are doing a good job of holding the wing to the plane, then what happens is the plane rises as well. Isn't that totally amazing? If I were to switch off Bernoulli's principle, I'm not going to do it, but if that little switch that I have and I switch off Bernoulli's principle, it's going to be a big problem for a lot of people. Do you know why? Yep. All the planes, any plane that's up in the sky, any helicopter, anything that's flying up in the sky will end up going kerplunk. Right? So that's why that little button is taped over so we don't switch it off by mistake. Right? So, but isn't that amazing? A principle like this makes all the difference. We're able to get tons. Think of how heavy a 747 is. Right? Tons and tons and tons and tons of metal. We're able to get it up in the air and like flying at 500 miles per hour. Who would have thought that metal can fly like that, right? All because of Bernoulli's principle. Or who would have thought that like tons of metal, like think of a cruise ship, how heavy it is. Heavier than, like bigger than many hotels. And a cruise ship is able to float and take people around. Something as simple as the principle of flotation enables that to happen, right? So without physics, at least the laws, none of these would work. Okay, so you're welcome to do this experiment at home. For those of you who have little rubber battleships or plastic battleships, or if you have little rubber duckies that you play with when you're in the bath, right? So you can have one of your rubber duckies here, little yellow duckies, right? It may be plastic. Another one here, or your battleships, and you've got a string here. Now you take a hose and you flow water between the ships, right? So water is flowing in here between these ships. As it's flowing between the ships, I would expect intuitively that this should push the ships apart. But if you do it right, that is, instead of directing the flow of water towards one ship versus the other, but exactly in the middle, so there's just a constant flow in between, what will happen is the ships will actually come together instead of going apart. Again, Bernoulli's principle at work. Because the water is flowing between the ships. Flowing between the ships at a greater rate than here. It's kind of stationary here. And it's silly thing. So it's flowing here. Since it's flowing here, what happens is that there is a lower pressure or a higher pressure? Lower pressure. So if there's a lower pressure between the ships and a higher pressure outside, what happens? They get pushed towards each other. Now you may have experienced this. I've experienced this on occasion. Like you're driving your car next to one of these 18-wheelers or whatever, right? On one of these winding mountain roads. Let's say you're driving out of Phoenix, and there's the wind associated with the travel of both of you. Have you ever felt a force that seems to be pulling you into the truck?
Yes.
How many of you have experienced that? Okay, so about half of you have.
Tried on an actual battleship.
Oh, you actually tried? Oh, really?
I was in the Navy. We got underway replenishment. You get two ships that are going 35 knots.
Okay.
15 feet apart from each other to transfer fuel and stuff.
Okay.
And they have to crank the rudders all the way.
So they're actually pulling outwards a bit.
So just keep going straight.
Yes, good point. So that's Bernoulli's principle. Extra credit to you, right? So for those of us who have not experienced a battleship like this, or don't have little rubber duckies, and haven't done that experiment, right? Extra credit to you, by the way, if you do the experiment at home with your rubber duckies and you videotape it, put it on YouTube, right? So, but the closest experience that I've actually had, and many of you have had, is doing this, driving along like a mountain road or whatever with a 18-wheeler or something, a big truck next to you. What happens is the air between your car and the truck is getting compressed, right? And so it's flowing faster, creating a low pressure zone between you and the truck compared to the outsides. So when I experienced, a couple of times that I experienced, I thought this is some kind of psychological effect until I came across this, right? I know. and then realize,
But
wow,
it's just my husband driving.
it is possible that he might be.
Isn't that what wind is? Is like when there's a lower atmospheric pressure, the atmosphere is rushing in to fill it, and that creates wind. All right,
Right.
so another car scenario. You know when you're driving in your car and it's real windy and you feel like you're getting blown to the side?
Yes.
Is that really the wind blowing you, or is that you trying to go into the...
I think in that case it's actually the wind against the side of your car, right? So here, the situation you're describing, you're kind of driving straight, you don't have another vehicle next to you and the wind scene. So that's just the gusting of wind that's applying pressure, right? So if you were a sailboat, it's like your car is the sail, right? Okay. Just a reminder for you guys to go over these multiple choice questions, right? That's your responsibility. And if you have any questions on any of them, catch me during the lab and we can talk about them. I'm